Hello everyone and welcome to our environmental engineering lecture. In this lecture series we will discuss water quality parameters in a simple and practical way. Today we will start with the first physical water quality parameter, solids in water. Solids in water are classified into three main types: dissolved solids, colloidal solids, and suspended solids. Now let us look at this table, which shows the size classification of solids in water. This classification is based on particle size measured in millimeters. Dissolved solids consist of molecules or ions that completely dissolved in water. Their particle size is smaller than 10 to the power of minus 6 millimeters. These particles cannot be seen and cannot be removed by filtration. Colloidal solids are very small particles. They are technically suspended, but they behave like dissolved substances. Their size range from 10 to the power of minus 6 to 10 to the power of minus 3 millimeters. And suspended solid consists of larger particles that are supported by buoyant and viscous forces within the water. Their particle size is greater than 10 to the power of minus 3 millimeters, and they can usually be removed by filtration. So, understanding the size of solids help us select the correct treatment processes in water and wastewater engineering. Let us now talk about water pollution. Water pollution is defined as the presence of impurities in water in such quantity and of such nature as to impair the use of the water for stated purpose. In simple words, water pollution means the water contains substances that make it unsuitable for the purpose we want to use it for. This purpose could be drinking, irrigation, industrial use, or domestic use. So pollution do not only mean the water looks dirty. It means that water cannot perform its intended function safely and effectively. Even clear water can be polluted if it contains harmful chemicals, microorganisms, or dissolved substances that affect human health or the environment. And to understand how many grams per liter are related to water volume and mass, 1 liter of water has a mass of approximately 1000 grams, which is equal to 1 million grams. Therefore, the unit milligram per liter is equivalent to milligram per 1 million milligrams of water. In this expression, the milligrams in the numerator represent the mass of solids, while the mass in the denominator represents the mass of water. For this reason, the concentration can be expressed either as milligram per liter or as part per million, ppm. So, concentration can be written as mass per volume or mass per mass of water. This equivalence is valid for water because its density is approximately 1 kilogram per liter. And if we talk about the sources of suspended solids in water, suspended solids can originate from both inorganic and organic materials. Inorganic suspended solids include materials such as clay, silt, and other soil constituents. Organic suspended solids include plant fiber and biological solids such as algae and bacteria. This material may come from natural sources such as the erosive action of flowing surface water. They can also originate from human activities, especially domestic wastewater discharges. In addition, immiscible liquids such as oils and grease can also contribute to suspended solids in water. Suspended solids are commonly found in surface water. So surface water usually contains significant amount of suspended solids, and the main source of these solids is surface runoff water flows over the land surface and carries with it various pollutants, including soil particles, organic matters, and other contaminants. As a result, suspended solid concentration in surface water tend to increase, especially after rainfall events. And if we discuss the impacts of suspended solid in water, suspended solid are displeasing to the eye and reduce the aesthetic quality of water. They also provide absorption sites for chemical and biological agents, which means the pollutants can attach to their surfaces. Suspended solid may be biologically degraded, resulting in objectionable byproducts such as odors and taste problems. In addition, suspended solid may include disease-causing organisms which pose a risk to public health. When we say the suspended solids are displeasing, we are talking about a human acceptance of water. Would any of us accept using water that contains visible suspended solids? The answer is no. Water acceptance is based on too many criteria. The first is psychological, and it is the most important one. The second is health related. If the water is rejected visually, we will not even ask whether if it is safe or healthy. In many cases, suspended solids in water contain organic material. This organic material can undergo biological degradation. As a result, unpleasant byproducts, bad odors may be produced. This is why water containing suspended solid may have an offensive smell due to the biological degradation of organic matter. In addition, suspended solid may consist of living organism or microorganism. Some of these microorganisms can be harmful or pathogenic. Examples include worms, parasites, and disease-causing organisms such as those responsible for schistosomiasis and cholera. For example, if organisms like schistosoma are present, they exist as a visible living organism in water and are therefore considered suspended solids. That is why controlling suspended solids is not only a technical issue but also a psychological and public health necessity. Now we will talk about measuring total solids in water. The total solids test quantifies all the solids in water, including both suspended and dissolved solids. To perform the test, we evaporate a sample of water at 104 degrees Celsius until it's completely dry, and then we weigh the remaining solids. The results are expressed in milligram per liter, which shows the dry mass of solid in a given volume of water. It is important to note that some colloidal particle may pass through the filter and will be counted as a part of dissolved solids. On the other hand, some dissolved solids may stick to the filter material. The outcome of the test depends on the size and the nature of solids, as well as the pore size and surface characteristic of the filter. Now, let's see how we determine the total organic content of solids. We measure the organic content in both total solids and suspended solid by firing the residues at 600 degrees Celsius for 1 hour. The high temperature causes the organic material to burn and vaporize, turning it into carbon dioxide, water, and vapor. What remains after the process is the inorganic residues. And to analyze the solid more precisely, we look at which part is inorganic or organic. First, we dry the sample at 104 degrees Celsius and weigh it to find out how much we have of suspended solid and dissolved solids. Then we take the sample, burn it at 600 degrees Celsius. The organic material burn and vaporize, turning it into gases and leaving nothing in the container. They get oxidized. The part that burn off is called volatile solids, and the remaining part is called fixed solid. We do this division for both suspended and dissolved solids. Suspended solids are important parameter in wastewater. They are used to measure the quality of incoming wastewater and to monitor the performance of various treatment processes. Here, incoming wastewater or influent means the wastewater that enter a treatment plant before any processing. According to the U.S. Environmental Protection Agency or EPA, the maximum allowed suspended solid in most treated wastewater discharge into the environment is 30 milligrams per liter. Now let's see an example of determining suspended solid. The tear mass of the filter and the container is 54.352, and we take 250 millimeter water sample and pass it through a filter pad. Then we place the filter in a drying oven at 104 degrees Celsius until it reaches a constant mass of 54.389. Our task is to calculate the suspended solids concentration of this water sample in milligram per liter. Let's calculate the suspended solid concentration. First, we find the weight of the solids by subtracting the tare mass of the filter and container from the desired sample mass. That is 54.389 minus 54.352, which give us 0.037 grams. Converting this to milligram gives 37 milligrams. The sample volume is 250 millimeters or 0.25 liters, so the suspended solid concentration is 37 divided by 0.25. So it's equal 148 milligrams per liter. 148 milligrams per liter. And here, example 2.2, 100 milliliter water sample is filtered using a filter with a tare mass of 0.254 gram. After filtration and drying, the filter weighs 0.263 gram. The same filter is then burned at 600 Celsius and weighs 0.258 gram. Calculate suspended solid, fixed solid, volatile solid. To find the suspended solids concentration, we calculate the difference in weight and divide by the sample volume. The difference is 0.263 minus 0.254, which equal 0.009 grams. Since the sample volume is 0.1 liter, the suspended solid concentration is 0.09 grams per liter or 90 milligram per liter. Now, if we burn the filter at 600 Celsius and weight it again, we get 0.258 grams. The weight decreases because some organic material volatilizes. To calculate the fixed solid, we take the new weight after burning minus the original tare divided by the sample volume. 0.258 minus 0.254 divided by 0.1, which gives 0.04 grams per liter or 40 milligram per liter. This is the fixed solid. And if we need the volatile solids are the part that burned off, we can subtract the fixed solid from the total suspended solid, 90 minus 40, which gives 50 milligrams per liter. This tells us how much of suspended solid were volatile and how much were fixed. Okay? The second important parameter we look at in water is turbidity. Turbidity tells us how many suspended solid are in the water. Usually turbidity is caused by this suspended solid. It's important to remember that color does not equal turbidity. The water can be any color and still be clear or cloudy. Turbidity is basically the ability of water to absorb or scatter or break light rays. When light passes through water, if there are particles that absorb or scatter the light, the water appears turbid. In other words, the more turbid the water, the less clear it looks. And here, turbidity tests are usually done for natural water or drinking water. The reason is that in these cases, it's more important to know what kind of particles are in the water and how they affect it, rather than the exact number of particles. For example, a few very fine or harmful particles can make the water unsafe or affect its clarity, even if the total amount is small. Okay? Remember, we cannot judge turbidity by color. Turbidity happens when light hits particles that block or scatter it, and the main cause is suspended solid. For example, if we take a clean flask of water and drop in a clean gravel pebble, does the water become turbid? No. But if we grind the pebble into fine particles, we find the water becomes turbid. This shows that turbidity is about fine particles dispersed in water, not just the total solid. So turbidity depends on the size and spread of particles. Large chunks don't make water turbid, but fine colloidal particles do. And if we talk about sources, let's talk about the main sources of turbidity in water. First, turbidity can come from the erosion of colloidal materials like clay, silt, rock fragment, and oxides from the soil. Second, it can come from vegetables, vegetable fibers, and microorganisms. And finally, chemicals like soap and detergents can also contribute to turbidity. And if we talk about the impacts of turbidity, first, turbid water is simply unpleasant to see and use. It also provides sites where chemicals can attach, which might be harmful or cause bad taste and odor. Tiny colloidal particles make water harder to treat, and disinfection becomes more difficult because the particles can absorb the disinfectant. Finally, when turbidity causing particles accumulate in stream beds, they can form sediment deposit in surface water bodies. So for revision, if we talk about the impacts of turbidity on water and its treatment, first, turbid water is simply unpleasant. People usually don't want to drink or use cloudy water. Second, fine particles, also called colloids, can carry chemical and microorganisms, some of which can be harmful. Third, turbidity makes disinfection more challenging. We use chlorine to kill microorganisms, but when colloidal particles are present, some of the chlorine reacts with these particles instead of disinfecting. This means we need to add more chlorine, like giving a sick person too much medicine. This is dangerous because chlorine's main purpose is to clean pathogens, not remove turbidity. When chlorine reacts with organic colloidal particles, it can form harmful or even carcinogenic byproducts. That's why it's important to remove turbidity before disinfection. Finally, turbidity can cause scale and sediment to accumulate in waterways, which can lead to clogging and deposits. Now let's talk about how turbidity is measured. The concept is simple. Turbidity shows the water's ability to absorb or scatter light. The harder it's to see through the water, the higher the turbidity. Historically, Jackson developed the first method. He put a candle inside a cylinder and placed a glass flask on top. Without water, the candle light was visible easily, but when water was added, visibility decreased. The harder it was to see, the higher the turbidity. Jackson created Jackson Turbidity Unit, or GTU, by calibrating with silica particles. For example, 1 milligram per liter silica blocked the candle light at certain level. This was 1 GTU. 2 milligram per liter blocked it more and called it 2 GTU, and so on. He graduated the flask and called it the Jackson Turbidity Meter. But this method had a limitation. Candle light differ, human vision is subjective, and it was not very precise. Modern turbidity meters using electronic sensors, they measure the intensity of light going into and coming out of the water. A pure water lets almost all light pass through, but the turbid water lets much less light through. Calibration now uses formazine, an organic compound, 1 milligram per liter. Formazine is 1 FTU, 2 milligram per liter, 2 FTU. Some devices use NTU instead. NTU, which stands for nephelometric turbidity. Jackson devices are rarely used today, mostly in museums only. In some older studies, naphthalene was used to a reference to create turbidity artificially for calibration, but today formazine is the standard used in modern turbidity meter. Basically, the more the light is scattered by particles, the higher the NTU reading. And turbidity in natural water can vary a lot, from just a few FTU to several hundred FTU depending on the location and season. In the United States, the EPA, Environmental Protection Agency, states a maximum turbidity of 1 FTU for drinking water. This stands make sure the water is safe, clear, and pleasant to drink. Okay, before we end today's lecture, let's quickly review the main points we discussed about water quality. First, Solid in water. Solid are classified into dissolved, colloidal, and suspended solid based on particle size. Dissolved solids are tiny molecules or ions less than 10 to the power of minus 6 millimeter, invisible and not removed by filtration. Colloidal are small, behave like dissolved substances, size from 10 to the power of minus 6 to 10 to the power of minus 3 millimeter. Suspended solids are larger of 10 to the power of minus 3 and can usually be filtered out. Knowing the size of solid help choose the right treatment process. And for measuring suspended solids, we take a water sample, dry the residue at 140 Celsius and weigh before and after. The difference in weight divided by water volume give me the concentration of suspended solid, milligram per liter or part per million. Some solids may be volatile, organic or fixed inorganic, determined by burning at 600 Celsius. And for water pollution impurities in water that makes it unsuitable for intended use. Even clear water can be polluted with chemicals, microorganisms, or dissolved solids. And for physical parameter of water, these are characteristics detectable by senses like color, turbidity, temperature, solids. They help us assess water quality visually by touch, taste, and smell. And for sources of suspended solid can be organic, like plant fiber, algae, bacteria, or inorganic, like clay, silt, soil, particles. And sources include natural runoff and human activities like domestic wastewater, and oil and grease can also contribute. And for impacts of suspended solid, aesthetic problem, water looks unpleasing, health risk, can carry pathogens, parasites, and harmful microorganisms. A treatment issue, solids may degrade biologically, causing odors and taste problem. Psychological aspect, human reject water that looks dirty regardless of safety. And for total solid and organic content, total solid equals suspended and dissolved solid. Organic solid determined by drying 140 Celsius and burning at 600 Celsius. And for volatile solid, it's burnt organic matter, and fixed solids, it's remaining inorganic matter. Suspended solids are key for evaluating incoming wastewater and treatment efficiency. For EPA limit for treatment wastewater, its limit the 30 mg per liter of suspended solids. Finally, for turbidity measures how much light is scattered or absorbed by particle in water caused mostly by fine suspended solid, not just the total amount of solid. Turbid water is visually displeasing and can interfere with disinfection. Sources include clay, silt, organic matter, and chemicals like detergents. Measured with turbidity meter calibrated with formazine result in FTU or NTU. NTU nephelometric turbidity unit measures light scattering. Always check size, type, and concentration of solids of treatment design. Suspended solid affect health, aesthetic, and treatment efficiency. Turbidity, not color, but indicates presence of fine particles. Measuring physical parameters is a first step in water quality assessment. I hope the lecture was useful and we will continue next time. Goodbye.